just to clarify things, this coproduct on homology of free loops, you construct for free loops which are immersions, and you told me that it's not really necessary to consider immersions, consider general situation.
Is that the question?
Yeah, it's a question. Is it, do I understand correctly that you mod out by small loops?
Yeah.
Yeah. Can you be a bit more precise?
Well, so he's asking a specific question about the, I was talking about strings, and there was a Lie bracket operation that corresponded to strings fusing together. And then I talked about a co-operation where a single string goes along and intersects itself and then breaks apart. But for this operation to be well defined, you have to modify the situation. And in either modification, the previous operation goes along with this discussion, so you still have two operations. And the reason is very simple. Well, I mean, this is not generally, it's just that if you look at the case of a surface, so this is, Turaev is the first one to discover this co-product. I mean, if you just are trying to, so the idea of the co-product is if you take any curve, you look at where it intersects itself. On a surface, you don't have to have parameters to make an intersection happen. A zero-dimensional parameter space is enough, one curve. So here's an intersection, and you break the curve like that, and then these are two elements. You can order them, and this gives you an element in the tensor product, and that defines this co-product. And you want this to be well-defined up to homotopy, or at least homologically well-defined, but see, up to homotopy, you can introduce a small loop like this. And the formula for the co-product is to sum over all the intersections, so there would be, this would be another term in the sum. So you'd have the first term and this term. But this is not zero. This is one of the components of the free loop space. So this would be an extra term which would render the thing not defined. So one method is to just divide out by a small loop. So take your free loop space, and if you're going in the higher algebraic topology, you can just mod out by the subcomplex as small loops, and in the tensor product, you'd have to mod out by the ideal. And then, nicely enough, the bracket operation of a family of small loops times anything else is zero, so that passes. And the other way is to work with immersion. So in the theory of immersed curves, this is a different element because you're recording the winding vector, and this is the topology of that space is different. So these string operations, there's like seems to be a vast number of them. You can start looking at all kinds of ways strings can interact geometrically. Anyway, that's so I guess we could have a discussion about any of the three talks this morning. Bob's talk, your talk, my talk, or, and then there's this weird title that I made up this title. I made up this title. The title, let's see, what is the title? The role of, first of all, this word homotopical algebra, I hate. It's ugly, but it's good to say it because it distinguishes it from homological algebra, because homotopic algebra sort of refers to studying with the ideas of homology theory nonlinear structures, where homologic algebra refers more to linear structures. And the idea, like it's the idea of the structure of an algebra, whether it's associative or not, or Lie algebra, bi-Lie algebra, and various kinds of nonlinear structures that might arise. And Maxime has done a lot of work in this direction about nonlinear structures like this using the methods of homotopical algebra. And in fact, his talk was about this as well. So I thought, well, does anyone have a question about, if they want to direct Bob or Maxime or me? If not, I'll ask Maxime a question. Okay. Yeah. Yeah, so.
In connection with Bob's talk, it's more an appeal than a question. This one. Namely, about applications of topology in computer science. And because there was a lot of talk here about whether P is equal to NP and at earlier times. And the main obstacle here is that we have their complications, which we feel are complex, but don't know how to put our fingers on. And there are a couple of examples, more than a couple, several examples, where using topological notions, one can actually formalize this and prove this. So the nicest example is about the decision complexity of Boolean functions, where Kahn, Sachs, and Sturtevant have a very nice paper where they prove that you can, in a natural way, assign to these a Simplicial complex. And if this Simplicial complex is not contractible, then the corresponding Boolean function has maximal possible complexity. So the topological complexity, actually that's a rather mild topological complexity of this topological object, is very closely related to the computational complexity, some sort of computational complexity of that Boolean function. And they use this to settle some conjecture which was open then for, I don't know, several years. So I think that it would be nice to have cooperation with topologists, because as you see, we can only think of topological spaces as Simplicial complexes because that's how we learned at the university. And so it would be nice to, you pointed out that you have, that maybe it's better to glue together tori instead because you get nicer objects. So I don't know. I just wanted to mention this as I think particularly important applications along the lines that you formulate.
I don't like to waste my time. I want to learn something while I'm here right now. So, Maxime, would you come and tell me about this supermanifold again and what the idea is? I think that would be interesting. Yeah, the small one. Yeah.
Geometry is not important.
It's not.
Okay. Now the story is that when you have some object, you have some parameters of your objects, but then you have some conditions or equations on these parameters, like manifolds, really manifold, and not anything else. And then you get gauge group. You have no, for example, what is a manifold to this? You have atlas of and but things glued together. So here it will be equations for associativity, and here change go to another covering. Net gauge group of some kind of equivalence relation.
What do you say, equations for associativity?
Oh, for example, I take vector space and get map from A to A, and equations it's two things. One product in one order is equal to product another order, and actually it's considered not a vector space, but let's say Cn. Because it's not already notion of vector space, it's complete Cn. And here JLN. You choose different bases of your space. Notion of vector space is already some identification.
N cubed parameters and n fourth equations.
Yeah, I get n cubed parameters, n4 equations, and n square things. It's really nice. 2, 3, 4. Yeah. No, it's like, in effect,
The right dimensions.
really deep. Yeah, because in fact, if you go and categories, yeah, so you have some kind of 3 types of things, and but in already in category theory, go something here. For example, have categories, kind of pre-category. You get set arrows, compositions of arrows, and there are conditions of associativity and compositions. Here it's well defined up to end of functors. But end of functors form again a category. Object of a category. So here are the natural transformations. So in category theory, you go one step here, get something, symmetry of symmetry. And what's the deformation theory telling that somehow miraculously for any object you can build infinite sequence which can be terminated on the left or on the right, but there are some natural things which explain why overdetermined system of equations still have solutions. And
What is this thing?
And this is super manifold, the graded manifold.
Very specific one,
Sorry?
It's very specific.
Yeah, so the different things, will be coordinates on the super manifold of different degrees responsible for deformation theory. And collection of relations between all these things is hidden in this vector field Q. It's square equal to 0.
So what comes after equations?
After equations?
Yeah, relations between the equations.
Yeah, some kind of tautology which you automatically have between equations. Tautology between tautologies. It's
Can you illustrate this with one example?
sorry?
Can you illustrate this idea with one specific example where you see the hierarchy of equations coming, or the hierarchy of the supermanifold coming?
Now,
Well, like, you want to do this example, associative, or you want to?
yeah, it's fine already with this example. It's,
Okay.
So here's a picture. You see there's something missing here. This n to the first power. Maybe n to zeros, but I don't know. So you get Cn. Let's consider tangent space to these things. We get hom Cn, Cn. So here I should write Cn to the fourth power to C.
Just about it.
Cn. Okay.
Does it keep going, or what?
Yeah, one can keep going, yeah, but so I don't know what really to talk about. Suppose I have a so all the story form differential graded Lie algebra, and this is sick. Our map here it's called Hochschild differential. So this map. So for example, here you can see the deformation. Suppose we have some product already, Cijk, which is a associative product, and want to consider nearby product. So then here it will be deformations of the structure constant. Here we kind of make infinitesimal change of coordinates. Then if you have an infinitesimal change of coordinates, then you get automatical transformation. And here there is any element of Cn get automorphism of algebra. So it gets, the product will not change. So there's something in the kernel, so a joint action. And here we get equations for associativity in nearby things, and at least in linear approximation, it looks, but you get not everything here. There is a next map which is, I will not write, it's pretty standard. It automatically says that what you get is equations, the right hand side of equations automatically satisfies some equations. So it's not sitting not in this space but in kernel. So it's this whole mystic idea of homological algebra for resolutions. I don't understand why, but it's how things work. Yeah, so naively you see only kind of small part. It's kind of naive part, and then the rest somehow naturally grows from this.
What happens to the negative?
Negative goes to, so there are two directions. Negative goes to topology. And here's more kind of algebraic geometry, supergeometry. So if things will be only negative parts, we'll have only symmetry. So it's essentially a homotopy type.
So I don't understand. What's the negative direction?
In usual cases, the story is the following. So when people discuss it, also the linear and so on, they all assume that this differential graded Lie algebras concentrated in non-negative degrees. So you get symmetries, data, and equations, and so on. But also there was a story, theory of rational homotopy type, which goes to sits in completely negative degrees.
But for this case, it doesn't exist.
No, but in this case you have something in degree -1, and you consider more complicated things like 2 categories, and you get something in degree -2. So if you go for
not for this associative form, but for other stuff.
No, for associative algebras, in fact, if you do straightforward things, you should stop here. You shouldn't put Cn here. And if you put Cn here, it has some miniq deformed category of modules of algebra, something like this. It's already has different meaning if you add this term. And in polycategory examples, it seems that you will have mathematical terms in negative degree, and also quantum field theory essentially is concentrated in negative degrees, so it's this homotopy type related to quantum field theory.
Then particularly obtain more and more complicated system of overdetermined equations.
Yes.
You should have some reason have solutions.
Yeah. Yeah, and in nice cases, homology of this complex will be finite dimensional, so you can understand it as whole somehow. It's different.
So this is an exact sequence, semi-exact.
Oh no, it's not just complex. Complex, yeah.
And is there some combinatorial significance to some dimension which appear?
Sorry?
Some nice generating function which come out of it?
No, there was a lot of nice things about this, especially this complex. There's really a whole story, what is going on. So it's.
But you said it was eventually exact, no?
No, in kind not eventually, but the story is that these complexes, which you can construct in different situations, very often they reduce to some kind of elliptic complexes, and they have finite dimensional cohomology. So more or less you have kind of finite dimensional manifold of parameters.
So the existence of each next error is a somehow non-trivial fact.
Yes, yes, yes. No. Oh, so, yeah.
What does this have to do with quantum field theory? Again?
It's in quantum field theory. It seems that one can describe this axiom of operator product expansion. One can define very neatly what is renormalization, regularization of this Feynman correlators and. Sorry?
From this example?
Yeah, in field theory you get all things go to negative dimensions.
Well, an object like this, but what are the groups?
Oh, groups, it's called, groups have something, get something like local fields. As, I don't know, in free field theory you have a field to take derivatives, to take some products, and put two dots, to put something like normal ordering. And so we can make some infinite dimensional vector bundle of it and with flat connection, and it will be the RAM complex of this vector bundle with flat connection.
But what is the statement of the smoothness? That any deformation of the first 2 or 3 levels can extend all the way?
No. The idea is that the kind of whole picture can be understood, at least in level formal power series, as you get some ambient manifold, super manifold, in which
Yeah, but
your object.
You mean if you take any point, you take any law, something like that,
Yeah.
and you just, at this approximation, you
Yeah.
change it by an epsilon, and then you can extend it all the way. You can continue. So you have something like this Hurstich law, which also satisfies some
Yeah, it's automatically
law
good.
about the law.
Yes, and this is.
And you deform it, and then
Yes. Yeah. That's good.
But so Rafa, what is super manifold? What is kind of
Super manifold.
what is relation with this complex? How is that related?
Yeah, no, just make it kind of vector space from this, and it will be a small neighborhood of a point in your super manifold. But then the idea is that if you can kind of reduce the super manifold only passing to this small part with the same homology, and it will not change the picture. So this complex is not something canonical. We can maybe write something different with the same homology. Yeah, also just some things that's in all this business, there's some level, it's important things are called operads. And operads, you can say, set of operations on a set. And you can compose them using trees. Suppose you have some binary operations, certain operation with 3 arguments, another operation with 4 arguments. So you can compose if you draw a tree. And these trees are exactly strata in Fulton-McPherson. It's a compactification of the following things. You take any manifold, take this nth power minus diagonal. Then you can add something to the boundary. You get manifold with corners, and it's independent from dimension. It's exactly labeled by the same tree, so this intrinsic relation of operads and manifolds in all dimensions.
What is the interpretation of this? Not trees if you take more ends, kind of. That trees, but not with one root. Is there also similar interpretation?
Just remove this thing, you get.
I mean, you can also interpret it as complexity, like simulation or something. If you have this kind
Can't hear you.
If you have a kind of structure which can grow in both directions.
Yeah. I don't know, in fact, yeah. This is, it's especially about points, something. And in fact, this geometric language, it helps to speak about algebra. So these days, I think that what is associativity? You consider this manifold, take Rn minus diagonals, take closure of this, and from this make operad go to chains, and this is associative algebras.
For n equals 1.
For n equal 1, yeah, R1 or 1 to n.
Oh.
I don't know. So it seems that if you want to think about the operates, then it's better to just consider this, not writing formulas, but use directly these manifolds. So it's a way to write. Okay. Oh, sorry, I cannot be more specific. It's a long story.
Topic.
I know. Oh, okay.
I have some question in topology, again arising from combinatorics. So it's about singular spaces, so I apologize. But so for various purposes, I mean, for us, for certain combinatorial purposes, spaces which, say, pseudo-manifold, where with much weaker conditions than being manifolds or spheres, behave like spheres. So let me mention two such conditions, and I would like to know if there is some topological reason for that. So the first condition, which is simpler, is that all the links, so locally, all the Euler characteristics look like the Euler characteristic of the spheres. So there are various conjectures that such objects behave like spheres for several combinatorial natures, and I would like to know if there is, well, we don't know how to prove it, and it looks that it relates to their topology. And the other example, which is behave even much more like spheres in terms of the so-called Stanley-Reasoner ring and other things, is a pseudo-manifold where all the links don't have a middle homology. So all you need is, well, in homology spheres, you don't want any homology except the top and the bottom. But here, you just want to exclude the middle homology, just for the even-dimensional manifold. So my question is, did you ever look at such gadgets?
He would be a good poker player.
And
Come on, Bob.
and I mean, is there some?
You have a lot to say about it. Just on you. I know you do.
Well, if you don't want to say it in public, you can just let me know privately. But
in your first question, you said if the links have the Euler characteristic of spheres, then the poly even is like a manifold or like a sphere? What did you say?
it like spheres in some combinatorial aspects.
Huh?
For some combinatorial aspects, if this is enough that it will behave like a sphere.
Like what?
Relations of phase numbers, upper bounds for phase numbers. And when it comes to the other condition with the middle dimension, then in much more algebraic notion, like the Stanley-Reisner ring, it satisfies, there is a notion of Stanley-Reisner ring, where if you, Stanley-Reisner or phase ring, it's a commutative algebra notion that after, that somehow, in the very special case of simplicial polytopes, it gives, when you mod up by a system of parameters, it gives the cohomology. But it exists for much more general objects. And for some reason, if you omit the middle homology, just this middle homology, then this ring behave in a very, very much like that of polytopes or spheres. I mean, it satisfies some hard Lefschetz and all sorts of things. And I wonder if there is some topological theory or some significance of this pseudo-manifold where just this middle dimension is omitted.
Definitely, yes. Right, it's the natural conditions under which you can define the middle intersection of all.
The middle,
Yeah.
but you can always define it, no?
No, if you have odd codimensions strata so that you can even ask the question, then you don't have a middle group. But if the middle homology group of those manifolds is 0, then you do again have one.
But for complex manifold, it's not always. Complex varieties, We don't have this condition always.
No, wait, maybe I didn't understand the condition.
You look at the links, or the links of every face. So this is a codimension K topological space. And if the dimension of this is even, then we want to exclude middle dimension homology.
Right, so for
Right.
algebraic variety, you
So
never
for
get such a thing.
so for an algebraic variety, it's never even. So it
No,
only
wait, don't go away.
right. No,
There's more. For 1995, you also get. No, Bob,
no. You mean the Euler characteristic business?
the middle homology business. Well,
Well,
let me tell you what needs proven, okay? If you have a space that satisfies your condition, then there is this, well, a manifold, its homology satisfies Poincare duality, right? And you can do a lot of things with that. Now, if you have a space that satisfies exactly your condition, his best homology theory, in my view, is defined and also satisfies Poincare duality. And you can do a lot of things with those spaces that you can do with manifolds. So you can find K-theory orientation and signatures, and you can go forever.
this is Dennis's Jugendtraum.
Yeah, my Jugendtraum, he did it. Yeah. But I mean, you have to find out more. I'm amazed that you can come up with that condition. It's a very deep, kind of unobvious condition. Right? Aren't you amazing? In some combinatorial.
Yes, I'm amazed as well.
Okay, well, you don't look amazed. You're a pro poker player. I wanted to just make one comment about why this very abstruse sounding topic is very practical, I think. There's this idea that in any kind of oh, this goes to pocket. I'm thinking about what I'm going to say. From a practical point of view, it's very easy to get non-associative structures. For example, numbers. If you multiply real numbers, they're not associative, because when you do it, you actually truncate somehow, and you start to multiply, and there's a little error there, and it's not going to be quite associative. Isn't that right? Huh?
Sure.
Yeah. So anything you sort of do, you take some kind of problem you're trying to compute, like some geometric problem, and you do some kind of grid, and you do some truncation. Like you take a Fourier series of a function, you look at the first 1,000 coefficients, and you write down a product. That'll have Fourier coefficients running to 2,000. You truncate to the first 1,000 again. That'll be a multiplication on the first 1,000 on functions with this limited approximation. It won't be associative. So, I mean, anything you do will lead to, when you do it practically, will lead to a non-associative structure. Now, he started talking about some fancy thing here. Doesn't matter the details of it, that would describe some aspect of the theory of associative algebras. But there's a remarkable thing that happens in this, which I wanted to get to in just a second. But this was a remark I made in my talk, that there's this way to correct errors in equations like associativity and other things if they're sort of morally still correct. I mean, the idea is that when you multiply these truncated things, the answer is the deviation from being associative, or the identity that you wanted it to be, isn't off by much. So, now in numerical analysis, I guess they assume that, just you'll discretize all these nonlinear phenomena, and then you kind of hope that what you get approximates the real thing, and that may be true. But there's an idea here which says you don't really have to give everything up, because I kind of suggested this idea that if you're multiplying some quantities, and I was talking in the language of topology, like I was doing A times B, and then you had B times A, and then I imagined there was some kind of a path between the two. So in other words, the answers, in this context, I'm saying the answers are close, and in this way you can build some kind of a path between the two. And the formalism that I'm imagining for the corrections is given with this differential from topology. So you can imagine that you're building up some ring structure of some objects that are going to approximate differential forms or something, or some other thing. They don't satisfy the identities you want, but you build in corrections stage by stage for the equations you want, using the fact that the answers are close together, and so what's in between is contractible, so you can solve these equations. And there's some hierarchical business, and actually it's quite complicated in a combinatorial way. This was developed by Stashev. But if you go back to what Maxime was saying, if you just take the idea of an associative algebra, and it turns out there's a natural construction that you're supposed to look at. You take the vector space, you take the components of the tensor algebra, and look at this thing, and you interpret the multiplication in here to give you some differential, and that gives you the first term here. Anyway, what was discovered is that all these corrections for associativity turn out to just be, in this example, the differential that you write down is just, let's say it starts off with, let's say I want to do this in the context when this already has a complex in it. This Cn is not just a vector space, but it's already a complex. So you have this kind of structure in it to glue things together. And the differential that he writes down here has got a first order term, which is the differential I'm assuming in C, and then it has a second order term, which is basically the tensor given by the multiplication. And then d squared equals 0 is exactly the condition that this differential respects the multiplication and the associative law. But now what's been discovered is that you can scrap this, and you can imagine having higher terms here in this business, and then you again write d squared is equal to 0, and it turns out that the higher terms you need are exactly all these complicated combinatorial corrections that make associativity true. You correct the associativity, and then you imagine higher order equations that would correct it. So in other words, you can be in a context where you are truncating your Fourier series of your fields or something and trying to regularize a problem. You create a non-associative structure, but you can, because the errors are small, you can build all these corrections, and they're very complicated in some combinatorial way. But conceptually, it's extremely simple. You're just building in a bunch of coefficients in order that this equation is true. So, in fact, when you look at things this way, the concept of an associative algebra is unnatural. Because when you re-express what it means you've found a differential that happens to only have first two terms. It's like you're considering a power series. You say, I'm going to truncate at size 2. So, but you should take them all. So in fact, the idea of this sort of abstract stuff sort of leads you to a concept of a corrected multiplication, from some abstract point of view, is quite elegant. So I see that this is one example of homotopic algebra. You can do the same thing for Lie algebras, for algebras which have products and compatible Lie algebras, and there are a lot of homotopical algebras coming up in some of the constructions of field theory, and this yoga of Kontsevich that was trying to talk about just says that you could re-express many complicated things in terms of this one equation. Well, he was calling it q squared is equal to 0. And I find this quite remarkable that this is possible, because the information in this is quite complicated. It corresponds to something very intuitive of corrections and corrections upon corrections. And my hope is that, I mean, this is a kind of pure kind of topology, in some sense, connection between topology and geometry. My hope is that that you might be able to apply this to this idea in some serious way to some of the questions about irregularity. So I just wanted to, so anyway, to summarize the remark, this sounded pretty abstract and the way he was talking about it, but if you actually look at any truncation of a nonlinear problem, you get into this. I mean, and people who work on this don't know about this. That's another weird fact. So I think it's something we should try to use. Huh? What? Good. Well, we have to prove something with this before we can convince this. Anyway,
after 6.
Yeah, I think we should. It's been a long day.